Okay, what we're gonna do today, two things. I'm gonna talk about what is a reaction in a lot of detail. And the second thing is we're gonna talk about chemical reactions, because you've got to be able to balance the chemical equation. And every stoichiometric problem we do from now on is gonna have a chemical reaction that needs to be balanced. Occasionally, if it's a really hard one to balance, I will just balance it so you won't spend a half an hour balancing. I'll just balance it for you. And sometimes, the reaction is super simple. For example, dropping table salt in the water and it dissolves. The reaction is sodium chloride, arrow, sodium chloride. Already balanced, right out of the chute. Those are two extremes. Everything else in the middle, you guys get to do. All right, first thing we're gonna do is, are there any questions about what's going on? Scheduling, now today and tomorrow, we're gonna have a dry lab. Because the schedule got messed up. And they claim tomorrow was a holiday, which it's not. It's Friday, like I already told you that already. And so rather than go back and redo the whole schedule, I just made dry labs for this week. And the rest of the schedule remains the same. Okay. Let's talk about what is a reaction. Now, the world goes around with two things going on. One, unstable things want to become more stable. So what you start with in a reaction has to be more unstable than what you want to end up with. Otherwise, it won't happen. Secondly, things like to become unorganized. The metric we're going to use for that is called entropy. So those are the two driving forces. Oh, the first one, the fancy name for that is called enthalpy. And entropy, those are the driving forces. Now we're gonna, later on in the semester, we're gonna talk about something called Gibbs free energy, which emboldens both of those. But that's what's driving the universe as we know it, particularly on this planet. Okay, so we're looking at
Are you recording?
yes, I am. See the little red dot up here? Right there,
Oh.
tiny. But lately I've been checking a lot. Okay, so that's basically it. Now, the unstable part, we are going to represent on a graph. This is going to be an energy. And the energy is enthalpy, but it's more understandable to call it potential energy. And this is just time. Okay. If I let go of this, what's going to happen? It's going to fall. All of you did very well. That's because the potential energy here is less than the potential energy here. So what happens, we converted potential energy up here into kinetic energy as it fell. So we go from high potential, unstable, to low potential, stable. And what happens is that marker actually heated up. The kinetic energy is called heat. Kinetic energy is the energy of movement. Now, our universe is constantly moving. Sometimes it's microscopic or very gross. Like a comet zooming through the sky. Okay, so let's represent on this graph the reactants and products. Notice the products are lower potential energy than the reactants. Hence, that means they're more stable. Now, what happens if we have like we burn methane, CH4, and oxygen, we end up producing carbon dioxide and water. Okay, so I can release methane from the wall, turning on the valve. Does anything happen? According to that equation, we're gonna get a reaction because we have oxygen in the air and we have methane. Why does nothing happen? Take a match, hold it. Nothing happens.
Gotta light it.
You gotta light it. How do you do that?
Light it. Or,
A spark, right?
start.
So we need energy to get the thing going.
Mm.
Just like a campfire. You have logs on a campfire, and they just sit there. You have to get a little fire going, which provides the energy for the bigger fire and the bigger one, et cetera. So that's what's missing from this graph. We have to show the fire, the starter. Now that fancy term for that starter is called activation energy. Notice something here, that we raised the potential energy of the reactants, made them even more unstable. So what happens is we break apart the bonds of the reactant. And those are all sitting here. And that's called the activated complex. Now, what that is, are all the atoms of the reactants taken apart. It's taken apart with that energy, that activation energy we put in there. So they're by themselves, C's, H's, and O's. Now, there's two places to go if you're in the activated complex to become more stable. You can go back to the reactant side or you can go to the product side. Both are more stable than the activated complex after we zapped it. And there's a ratio between products and reactants. It's called an equilibrium constant. And that's the ratio. Okay, so this is how much energy is required between here and here to input into that reactants to get it moving. Sometimes it's really high, sometimes it's very low. Let me give you a gross example. How do you make diamonds?
Press.
Of what? Carbon. Carbon. So you're gonna take carbon millions of years later with something still carbon, but it's not in the same structure. It's a tetrahedral structure in the diamond and a planar structure in the carbon. It's like charcoal. So which do you think is more stable? The charcoal or the diamond? thinks it's the diamond? Raise your hand. Okay, majority says diamond. No carbon takers?
Wait, did you say potential in
Mm.
it? Oh, stable.
Well, that's to do with the What about the carbon? You just invested thousands of dollars for that diamond on your finger. Guess what? Carbon's more stable. What? Ferguson, are you on drugs? Okay, with. So the activation energy should go from. I didn't draw that right. So the activation energy required to get over this hump is huge. But the carbon is more stable. So in your lifetime, your diamond ring is going to be a diamond ring. But it's a conundrum. The carbon is more stable. It's a flat, planar structure, which is inherently more stable than a tetrahedral. Diamonds. We're going to have a lab on that, not with diamonds and carbons, but on structure. Okay. Now, who has heard of the term catalyst? A number of you had. Do you remember what it is?
Something that sparks the initial reaction,
What does it do again?
something that sparks the initial reaction.
Yeah, so it's very, very similar to that. It speeds up the reaction, okay? And it does it by something very clever. It lowers the activation energy. So the same amount of energy before is not needed anymore. Now, catalysts in our world are horrendously important. An organic catalyst, I have a whole subunit on catalysts in my 306 class. We have millions of catalysts in our body called enzymes. So enzymes are organic catalysts. What our body does takes glucose molecules. It's not glucose, it could be fructose. It could be a fat. That has to be converted to glucose first through gluconeogenesis, but glucose. Interesting, glucose gets converted to fructose inside the first cycle. Then it's broken down, all the way to the end third cycle to an energy molecule called adenosine triphosphate, ATP. And there's a whole bunch of enzymes that does that. Now, the same thing can happen if you strike a match. The same reaction, it's combustion. Our bodies do it at 98.6 degrees, not at 600 or 700. So catalysts do things that require a lot less activation energy. And if they're made up of a protein, it's called an enzyme. So catalysts lowers the activation energy. That also speeds it up because more molecules have that lower activation energy and the higher one, so it can move along faster. So catalyst, everyone says catalyst speeds up reaction. It does, but it does it by lowering the activation energy. That's the important part of that. Now, there's two things that's going on in a reaction. Speed and stability. Speed is a variable that the reaction goes from reactant to product. Like on the diamond and carbon. Kinetics of that are extremely slow, just because the activation energy is so good. Okay, and then you also look at the difference in the stability in terms of potential energy. So those are the two main things going on in a reaction. Speed, which is called enzyme kinetics, if we're doing enzymes, or just plain old kinetics if we're not doing enzyme kinetics. And the other one is called Gibbs free energy. You don't need to worry about that now, we'll get it all unit. Okay, so we have unstable reactants going to more stable products. Now that difference here where the difference between what we start with and what we end with is called Gibbs free energy. So what we're doing here is we are converting okay, so the original potential energy is decreased by some amount, calling it Y. And that Y is the Gibbs free energy. Now, potential energy again is the energy of movement, kinetic energy. So if we decrease the potential energy, it's converted to kinetic energy. How does kinetic energy manifest itself? Daily life. Called heat. Heat, and so when things move, that's heat. Molecules moving. This is how a microwave works. Speeds up the movement of those molecules. Okay, and usually that interconversion between potential to kinetic energy is heat. So let's go back up to the methane and oxygen producing carbon dioxide and water. We've left off heat. And that's a dive underneath the covers on what's going on in a reaction. It's an interchange between different energies, potential and kinetic. It's an exchange between things becoming more stable. And a big part of that is providing adequate activation. If you don't give it enough, it can't get over the hump. Nothing happens. For example, we have a match. The match does not light unless the activation energy is high enough to get over that hump and form the activated complex. Because there's heat in the air. When there's no heat, it's called absolute zero. That means it's minus 473 degrees Fahrenheit. Minus. That means no movement at all, no heat. On your mind, I want you to think movement, heat. Okay. There's a lot of detail in this. A lot of detail. Okay. So are any questions about that? You've probably not seen it that way before, except for possibly. Yeah,
So when you go from reactant to products. Does it'll always be more stable? Or does it ever go the other way?
that's a good question. Who's heard of a coal pack? Anyone?
No one.
Like the.
How do you work a coal pack?
Very good.
There's an ampule, glass ampule in there, you have to break. Then it gets colder. The opposite happens. So how can that be? Remember, there are two factors that determine this. Potential energy, what's the other one? Entropy. So the entropy then drives the reaction. The opposite happens. So yes, opposite can happen. And that's called an endothermic reaction. It gives off heat is called an exothermic reaction. But most of the reactions are exos. There's not a lot of endos, but they're around.
What about the diamond carbon? Isn't the diamond a product of carbon?
An exothermic reaction. Because carbon's lower than diamond.
But it's
The activation
it's still a
it
product.
requires a whole bunch of activation. That's why the reaction is so slow. So was that your question?
Not really, but I think I understand.
Yeah,
Can you explain how the cold thing works again? Just like.
Yeah.
with the-
okay, when we get to Gibbs free energy stuff, it's not gonna be potential energy, it's gonna be Gibbs free energy. That's equal to okay, so this is enthalpy, which is potential energy. This is entropy. Entropy is a measurement or a metric for randomness. Now, if you come to my house, open my sock drawer, you're going to see a lot of entropy there. As opposed to my second wife's drawer, which were perfectly aligned socks, coordinated by color and season. I have two drawers. I have a white drawer and a black drawer. When I reach into the white drawer, there's just a bunch of white socks in there. I know I'm going to bring up two whites. Same with the blacks. That's my organization. And that's why she is my ex-wife. Just. She was the hospital administrator for the Fairfield Hospital. She's number one in the whole hospital. So being OCD is really good if you're a manager, not a spouse. Not a spouse.
Shade.
Okay, so anyway, entropy can overcome enthalpy if there's enough of it. And it's also a function of temperature. Higher the temperature, the more enthalpy. So you can overcome a normally not favorable reaction by increasing the temperature because the entropy goes up, which overcomes the enthalpy to U. This is called thermodynamics, you guys, by the way, FYI. Okay, so what the reaction looks like. That we have reactants here, products here. And to do that, because the products are more unstable, you have to have entropy come into the picture, which is a driving force. It's always the driving force, but it depends on how much it is compared to the other one, the enthalpy. Now, there are whole courses you can take if you're a chemistry major on thermodynamics. In fact, you're required to take that course to graduate as a chemist. I mean, it's a whole semester just on thermodynamics. And, you know, the big thick book to go along with it, $180 book. Okay, so that, but again, it's more the exception than common. But they do happen, like a common example, the cold pack. Shouldn't get cold, it should get hot. Okay. So what I want to talk about now is related to this and our dry lab. Now, if you look on the dry lab I passed out, I have practice on hand file unit 1. Thank you. And this is very easy to find online, more practice, or you can check GPT at all. ChatGPT will actually create worksheets. Okay, so let's go back to our methane. This is called a combustion reaction. And again, it's very common. Every mammal, including us, goes through a very complex combustion reaction. It's called carbohydrate metabolism. Simpler animals like yeast go through a shortened version. They go through the first part of it, called glycolysis. And they don't get as much energy out of it. They get like 3 ATP molecules as opposed to 28 in the long cycle. Okay, now there are 2 ways to do this. I'm going to show you the most popular way to do it. If you're interested in math, if you go to the miscellaneous files on Canvas, you'll find a method using your TI-84 calculator using matrices. Now you're going to have another extra credit opportunity in Unit 1. I'm going to give you a very hard equation to balance. It takes most people about 90 minutes to balance it. It's seemingly simple, but it's not. Now you can do it that way, the guess and check way, or you can use linear algebra. And it takes 32 seconds to do it on your calculator. That much difference. It's amazing. Okay, so we're using something called guess and check. So there are 2 kinds of numbers in the equation. There are coefficients and subscripts. When you balance a chemical equation, you only change the coefficients. You don't touch the subscripts. That is totally off limits, no exceptions. So these are called coefficients. Right now they're 1. And if it's 1, you can leave it blank if you want. Now, the first step we're going to take an inventory of the atoms, not the molecules, the atoms. Okay, so on the left, we've got carbon, hydrogen, and oxygen. And on the right, we've got carbon, hydrogen, oxygen. Okay, how many carbons do we have on the left? One. How many on the right? One. Okay, how many hydrogens on the left? Four. On the right? Two. Not balanced. How many oxygens on the left? Three on the right. Notice I chose from all places on the right. So there are two places when we get oxygens. You have to add those up. Okay, so now what do? We took an inventory and found out this is not balanced. Well, remember, we can change the coefficients to balance it. We can't change this subscripts. Okay, so let me so what we're going to do is we're going to guess. Then we're going to do the inventory again. So guess inventory. That's the check part. Guess inventory until the numbers on the left equal the numbers on the right. Now this can be quite easy or horrendously hard, like the extra credit problem. Okay, so what do you want to change? We shouldn't change the carbons because they're already balanced. So there's oxygens and hydrogens left. Well, hydrogens are only in one place on the right. That's what the water. So what if we change this coefficient to a 2 now? Inventory again. Okay, carbons remain the same. Hydrogens are now 4. What about oxygens? Well, we have 2 here and 2 here, so that's 4. So oxygens are balanced again. Hydrogens are, though. So what can we do now? Hmm? Did you say 2?
Yeah.
Where are you going to put it? Okay. And put it on the left, that'll give us 4 in the way. 4 in the way. Take inventory again. That's 4. Everything is the same. So now it's balanced. Only now. So you can leave the ones up there or take them off. As it defaults to 1, there's nothing in. Now, this may seem counterintuitive. And most people who've never done this before feel that way. Now, I've done this, the first time I learned about balancing equations was in 1963. I was in high school then. That's when I first learned about balancing equations. And I don't remember an aha moment. But a lot of my students will go, oh, I get it now. Now, this is a very organized way of balancing an equation. I've seen a lot of teachers do it very awkward. This isn't awkward at all. It's just time consuming. Just keep changing stuff to see how the numbers work out. Okay, all right. Shall I do another one? Over 10? All right, I'm going to do one that you're going to have an experiment to go home to tomorrow morning. Okay, we're going to take gasoline and burn it. So H18 is octane, which is most of gasoline. Gasoline is very complex, got a lot of stuff in it. There's benzene in it, xylitol, it's got a bunch of stuff in it. Mostly octane, octane. That's where they get the number 92 octane, 81 octane, etc. Is how much octane is in there. Now notice something about gasoline. This also applies to diesel. When we burn it, we are making water. So tomorrow morning, when you start your car, I want you to run around the back and see what's coming out of the tailpipe. Guess what will be coming out of the tailpipe? Water. Right there, that water. Now, if you wait 15 minutes and run around the back and look at it, where'd the water go?
Yeah, that,
Hmm?
just, yeah, evaporating.
Yeah, it's not steam, so you're gonna see this thing. Still there though. Okay, so do an inventory. We have carbon, hydrogen, oxygen. Okay, we have 8 on the left. One on the right. Right away, unbalanced. 18 hydrogens, 2. 2 oxygens, 3 oxygens. Okay, so we got a lot of futzing to do on this thing. Okay, where do you want to go first? There's kind of a nice way to think about this. Do the simple ones less. Change the complex ones first. So let's change the gasoline, the C18 one. Let's fix that one. How can we fix that carbons?
The 9,
What about 9?
Said, carbon 18 with.
Hydrogen, that's right. We changed that. It's going to change hydrogen. So let's leave that at 1. And what about carbon dioxide on yours?
That's. Right.
Okay, well, let's make that 8.
wait,
Inventory again. So now we have 8 carbons, but we also have 16 and 1, 17 oxygens. So we fixed the carbon issue. Let's work on the hydrogen issue. Okay, we have 18 and 2. How can we fix that? Someone said 9. Where? That's right, where though?
Oh, in
It's 9 in front of the water.
there's an oxygen on the right.
Yeah, the water contributed 1. Fix it from 16 to 17. Okay, so let's see here. That makes that 18. Now the water. I mean, not the water, the oxygen. Okay, we have 16 here, 9 here, that's 25. So everything is fixed except for the oxygen. Let's fix that. Let me add, so far we've been doing integers. It also does fractions. Do you have any ideas? Okay, oxygen comes in twos.
12.5.
Oxygens on the right are odd. Is there any way to make an even number into an odd number? Yeah,
What time? Times is.
yeah, so, or 25/2, right? Is that what you're saying?
Yeah.
I heard you say all the right numbers, I was making sure it's a fraction. So some people teach this, saying there's no fractions allowed. Which is true, but if you can balance it using fractions, you just clear the fractions afterwards. So we're gonna multiply the O2 by 25/2. 12.5. 12.5, 12.5 twos is 25. Times, okay, so we're gonna multiply 2 times 25/2. So the twos cancel, leaves us with 25. So now it is balanced. But we have a fractional coefficient. So we have to change it so there are no fractions there. Any ideas how to do that? Yeah. Multiply everything by 2. Perfect. Okay, so 1 times 2 is 2. 25/2 times 2 is what? 25. 2 times 8. 2 times 9. Now let's take inventory, make sure it's still balanced. Okay, so we've got 16 carbons. 36 hydrogens. 50 oxygens. 16 carbons on the right. 36 hydrogens. And we have 32 and 2 is 32 plus 18 is 50. So it's now balanced. So fractions are fine to get you to balance the thing, but you can't leave them. And no, I'm trying to think, I would say about 95 to 99% of the time, you clear the fractions by multiplying by 2. So typically the fraction is something over 2. So to make it into a whole number, you just multiply it by 2. Yeah,
I zoned out when you wrote 25/2. I understood how you got that, but what did you have to do to
clear it.
clear it again?
We have to multiply the denominator,
Yeah,
which is 2. So we multiply the whole thing by 2, and then the denominator goes away.
when you mean whole thing, do you mean just
Is it the coefficients though, not the subscript, right?
everything?
Yeah, we're dealing with coefficients here, so we. See, that becomes 25.
Yeah, but you multiply everything,
You have to do everything.
every,
Think of it as an equation. What you do to the left, you got to do to the right. In fact, the second way of using matrices, you actually form a system of equations using the elements of the reactants and products. It's a really nice way to go. In fact, that's the first week of taking linear algebra. That's what you do. It's the big example is balancing equations. Okay, so what do you guys think?
I don't
Huh?
know.
Another example. Okay, if you look at your homework or your Roy Lab homework,
oh, yeah.
I want to caution you to do number 9 last. It's at the bottom anyway, but that's probably the hardest one of the bunch. Hey. Now, there's something else about a chemical equation, let's just talk about here. You'll see, you'll see these GLSs, gas, liquid, solid. They don't come into play in terms of balancing the equation. They're just there to describe the state of that particular component. Don't figure it in, don't count G's in the inventory or L's.
What about, the bracket and then the four, like, what about? Like on number 7? Is there a difference between oxygen? Or I'm guessing the bracket 4 means oxygen and hydrogen. Both.
Yeah, let me talk about that.
That's
That's
what it means.
okay, let's just look at, see, that was a chemical, and we needed to figure out how many O's, H's, and S's. It's got parentheses in there. Is that kind of the gist of your
Yeah,
question? Yeah, what about the parentheses? The parentheses means that's a group. SO4 is called sulfate, and it's a group. So that means there are 2 of these. That's what the parentheses 2 means. So if we add these up, how many oxygens are there? How many S's? And see, the 2 only affects what's in the parentheses, nothing else. So the 2 does not apply to the H, so there are 4 H's.
you kind of multiply it.
Use a distributive property, yes, we multiply. So we go. Now there's nothing there, that means there's a 1 there. Now, whenever we're doing things in chemistry frequently, and in math and in physics, whenever there's a 1 involved, it just kind of goes away. Because 1 times anything is itself. 1 times 4 is 4. 1 times a million is a million. It's itself. So when you're doing inventory, like, okay, our inventory is going to be sodium, hydrogen, sulfur, and oxygen. Just keep in mind that whenever you see the parentheses, the subscript for the parentheses applies to everything inside the parentheses. So here we would say 2 sodiums, 1 sodium, 4 hydrogens. This is a 2 here. 2 hydrogens, 2 S's, 1 S, 8 oxygens, 4 oxygens. Then we start changing the coefficients.
Professor, what about number 6? It has a parentheses S.
That means it's a solid.
Oh, right.
Remember you had SLE, solid, liquid, gas.
Just ignore those while they're.
Yep. One of these days, I need to go in and fix that. Like, get rid of them. Also, in number 2 and 4, there's a positive sign and negative sign, superscript. Ignore those. Okay, well, that's what I wanted to cover today, and we're gonna go into our dry lab. So, if you all want to do Thursday's dry lab here and not come to lab tomorrow at all, So what if, do you think we need to go upstairs? Is it too hot in here?
It's fine. Yeah, it's spaces.
Huh?
Yeah, everyone wants to do it together. Spaces.
That's right. We have to split them. Also, you can work out there. There's out there to the left. Where the left. So, yeah, it's.
Yeah, that's right.
I keep the sign of-
Yeah.
Where's the- Oh, this is the tournament? All right, let's start on this. We'll come back.
Yeah. You got this?
Yeah, that's what I want. Take both. I don't think it's.
And where the.
I just think that has more stuff.
First two.
This one is either. That's just explaining whatever is to break, but.
Right. Yep, we try that, so once you're done, it's like that. Four.
This can't be the process, you know.
If I got that. I think it was when he was saying this, to balance. If one. Yes. Both. We do get more here. Also. These are. No, I already. One, it was two. I was like, I could write it down. Yeah, whatever. Yeah, I think it's a good one. Oh, yes, yes, the bus. Okay.
It's important. Yeah.
Yes.
Come back. You come back. You can do it.
Yeah. Thanks.
It's like you need space to be your top. So I'm still moving in.
Yeah. Just one.
Yeah, so you're gonna.
Did you finish it?
Yeah, I finished it all. I finished the whole thing yesterday.
Okay, so you need to do a conclusion.
Okay,
All labs need a conclusion.
okay. I can do this.
And you did a good job. Starting the grade is in the 11 and 11.
Professor, is there any additional documents you can pass out with Brad?
I have,
Okay. Nothing else for Friday. This. That's something to be. Yeah, we're going. Here. Six. Well, we're gonna go over this tomorrow. Oh, okay. Future. Okay. Got it. So on this one, it is. Yeah.
so I have, this is.
Yeah, it's this morning and.
You're in the first.
All right.
These fun.
Nah.
Then you wait for-
Yes.
That's the one. Right? Yeah, the first, yeah, it's the one to come. So technically, this is over.
First you gotta set it up.
You have this.
What do you mean? One. And that one's, wait a minute.
Okay.
See, it's already new. What's with these negatives and positives? I know they didn't know how to do it. Oh, you were negatives. Thank you.
And put a-
Hey, it looks like it's already balanced to me.
and name
Is there one and both? Or am I?
I think we're balancing that.
these.
Well, if they said ignore.
Is that-
Everything's planned for me.
We're already confused. I don't know why it says that.
That's what I was
They
just,
think they could do
I
this.
was looking at that too, I'm like, but it's already balanced. It's, something similar. Yeah, what is that? So, I'm gonna go draft. I like. The whole like.
Did you?
Yeah, I said, I would try one.
Because it's already.
Yes, it's been years. But
It's already-
principal, right, the chat, the.
So that makes sense.
They wanted.
But you know what I think too? You also said to ignore the signs. But.
Here's the trial.
Okay, all right,
For the.
okay, we'll double check. Let's go to the.
So target. This is what.
I have.
Yeah, check it.
All right, cool. Got it, 1-1. That's what we thought.
This is all the report.
Let me turn this off.
Okay, number 3.
Yes. Oh,